Alright guys, welcome. Sorry I'm getting this out to you guys late. I had to head home right after school, or at an appointment right after school, and now I'm home. So I'm getting this out to you about 4 o'clock on Monday, or I'm recording this at about 4 o'clock on Monday. And so hopefully it's too late and you get a chance to watch it. We're going to be talking about polynomial factoring techniques in this video, but before we dive into factoring, I want to talk about end behavior, which is something we didn't mention in the last video, something I didn't talk about, that we could have talked about in the last video, but the last video was pretty long, so I'm going to talk about it now. And so end behavior is just asking what happens to the function's values when you plug in a very large and positive number, or when you plug in a very large and negative number. So really this is kind of like asking, what happens as you move to the right? So be to the right on the graph. And this is asking, can't spell. To the right. And this one is asking what happens as you move to the left. Use a different color for that. And our notations look kind of like this. And the order you do these in, it doesn't really matter. It's just that you have to talk about what happens to the left and what happens to the right. In this case, to the left is our first one. This is as x approaches negative infinity. So you're plugging in very large negative numbers. And the other one is as x approaches infinity, as you go to the right, what are your values doing? Okay. And for polynomials, the end behavior is determined by the leading term. This is for polynomials. Which is the highest power and the leading coefficient. So the leading term is the a sub n, x to the n term. Okay, so based off of the fact that we're looking at that highest term, we've got basically 4 scenarios that can happen. And the scenarios boil down to the whether the degree is even or odd, and whether the leading coefficient, that number in front, is positive or negative. So if you've got an even degree polynomial, then you're going to have both of your ends of the polynomial going up to infinity, or both of the ends of your polynomial going down to negative infinity. So that the even degree, remember this means that the highest power, so this is the highest power, is even. Power is even. For example, x to the 6th, x to the 8th, and so forth. Right? So that you have an even degree polynomial means that you're going up to infinity or you're going down to negative infinity. What tells you which way you're headed? Well, that is determined by the leading coefficient. If the leading coefficient is negative, then you're going down to infinity. Okay, and if it's positive, then you're going up to infinity in either direction. So the key with even degree is that both ends are going to be going the same way. Okay, either both up or both down. When the polynomial is an odd degree, now you're having opposite end behavior. One end will be going up and the other end will be going down. And it could be going up and to the right, or down and to the left, or it could be going up and to the left and down and to the right. Down and to the right, up and to the left. So these are your 2 options. What's going to tell you which one it is, again, comes down to the leading coefficient. And you can see over here when the leading coefficient is positive, you've got end behavior where both are heading up. Or excuse me, it's going to the right and up, and it's going to the left and down. So for example, the polynomial x. If you remember what that looks like, it's a straight line. As you head right, you go up. As you go left, you go down. X cubed. As you go right, you go up. As you go left, you go down. It's just steeper than x. And it curves, kind of zigzags in the middle. And if you flip the sign on the leading coefficient, then you're just getting this opposite end behavior over here. You're going right and down and left and up. So this would be like, negative x cubed. would be flipped. So that's looking like that, okay? All right, I'm going to erase some of this stuff on the slide. Now, to remember, to kind of help you remember these, leading coefficients have an effect. When the leading coefficient's positive, then you're always ending positive. As you go right, you're going to go up, okay? When the leading coefficient is positive, as you put in positive answers, you get positive answers back out. So a positive leading coefficient guarantees as you go right, you go up, okay? Now, whether or not you go up as you go left or down if you go left, that depends on whether it's even or odd. Even, both directions are the same. Odd, they're opposite, okay? So if you do remember positive leading coefficient, right up, no matter what, then you just decide based off of the degree, are these both up if it's even, or one's up and the other's down if it's odd. And then if it's negative leading coefficient, that says that as you go right, you go down. This is right and down. This is right and down. Whereas the previous one was right and up. And up. And you can see that over here, as you go right, you go down. Doesn't matter if it's even or odd degree if you've got a negative leading coefficient. Now, again, remember, if it's even, both are headed the same way. And if it's odd, they're in opposite directions. So if you just remember that if it's negative, I go right and down, then I can decide, are they both right and are they both down? If that, then it's an even degree polynomial. If it's an odd polynomial, odd degree polynomial, then they're opposite, left and up, okay? And so these are kind of the rules to remember. It's some combination of these, you know, 4 things. You either have a positive, I have a positive leading coefficient, and an even degree polynomial, positive leading coefficient, odd degree polynomial, negative leading coefficient, even degree polynomial, or negative coefficient, and an odd degree polynomial. And either way you remember this, the leading coefficient's positive, that means you go right and up. Then you decide both up or flipped based off of the even or oddness of the degree. Or if it's a negative leading coefficient, you know you go right and down, and then you decide both down or right down, left up, based off of the even or oddness of the degree. Either way you want to think about it, will get you there. Okay, so that's end behavior of polynomials. Okay, now let's look at factoring techniques. So what the importance of factoring? So remember that a factoring polynomials gives you the zeros, that the factors are the zeros of the polynomial. They're one and the same. The zeros of a polynomial will tell you what the factors are, and the factors of a polynomial will tell you what the zeros are. That is how we determine zeros, basically, is by factoring techniques. Another way to say this more succinctly is that p of x equals x minus r times some other polynomial, g. So g is another polynomial. If and only if you plug r in and you get 0. And you should be able to see that's the case right here. You know, r minus r, if you plug that in, times g of r. Who cares what g of r is? Because this thing right here is 0. And 0 times any number is going to give you 0. Right? So x minus r is a factor means that r is a 0. So factoring polynomials is crucial to finding where they cross the x-axis and are equal to 0. And we'll find that factoring polynomials or determining when they're equal to 0 is a powerful technique for solving lots of things, okay? So oftentimes you'll try to figure out when are two equations equal to each other. Well, it makes the most sense to write it as a polynomial, set it equal to 0, and factor it and solve. So, for example, this polynomial x times x minus 1 times x plus 3 has 3 zeros, one at 0, 1, and another one at negative 3. So that means it crosses the x-axis 3 times. So we have 3 crossings, 0, 1, and negative 3. And so those are our 3 zeros, and we can kind of sketch a graph from that. Because we know that it's got to cross 3 times. at -3, 0, and at 1. And we also know from looking at this that it's, x cubed plus stuff. And so we know that x cubed is an odd degree polynomial and a positive leading coefficient. So that tells you its end behavior looks like that, right and up and left and down. So we can kind of sketch this thing without actually, knowing too much more than what the zeros are and its end behavior. That gives us a rough graph of the thing. Now, where these, highest points and lowest points are, we don't know that without doing some calculus, which you'll do next year. But from this, we can at least figure out where it crosses the axis. Okay, so techniques for factoring higher order polynomials. First and foremost, always try to factor a greatest common factor if there is one. For example, x to the fourth minus x cubed has a greatest common factor of x cubed because there's x cubed in this and there's an x cubed in x to the fourth. So if you pull x cubed out, that gives you x cubed times x minus 1. See that this equals what we started with by distributing the x cubed back in, and you would get x to the fourth minus x cubed. Okay, so if you can factor a greatest common factor, do so. That simplifies your life. If a polynomial has a quadratic factor left, then you want to factor it like a quadratic. That means either difference of perfect squares or guess and check, however you can factor it. Factor a quadratic factor, and remember that not all quadratics are going to factor. For example, x squared plus 1, this one doesn't factor, it doesn't reduce. So here's an example of x to the fourth minus x squared, and we factor the greatest common factor out, which is x squared, because there's an x squared in that, and there's an x squared in x to the fourth. And that leaves us with x squared minus 1, which further factors, because it's a difference of perfect squares. So you can see x squared minus 1 breaks down into those two factors, x plus 1 and x minus 1. So you can see the three zeros that result from this are 0, 1, and -1. Okay, so those would be your three zeros from reading this. So x equals 0, x equals -1, and x equals 0 for this polynomial. And then if the problem is a quadratic in disguise, then you want to factor it like you would a quadratic, which means you do your what multiplies to the constant and adds to the middle term. And so, like, for example, x to the fourth minus x squared minus 2, this is a quadratic in disguise because if we take this middle term and we square it, we get this one over here. So just the x's, forget about the coefficients that are there. Just x squared is x to the fourth. So this is actually factorable like you would have, factorable like a quadratic, meaning we can write it out as x squared minus 2 times x squared plus 1. To see that's actually equal, let's FOIL it real quick. X squared minus 2, x squared plus 1. And so the x squared multiplies, and that gets us x to the fourth. X squared and 1 gets us x squared. -2 and x squared is minus 2x squared. -2 and 1, that's going to give us minus 2. And you can see from this we get x to the fourth minus x squared minus 2, which is what we started with. And then the x squared minus 2 can factor further into x plus root 2 and x minus root 2. Even though it's not a perfect square, difference of perfect squares, it still factors just like a difference of perfect squares would. And the x squared plus 1 factor that's left doesn't factor further. Okay. We're going to look at two more techniques in the next couple slides. One is a sum and difference of cubes, and then the last one is going to be factoring by grouping. Okay, so sum and difference of cubes. First off, I would like you to expand this expression. Take a little bit of time, pause the video, expand it out for yourself, and then we're going to do it together. So you pause the video now and then replay it once you've expanded it. Okay, hopefully you went through expanding it yourself. So I'm going to just show you the way that I expand this kind of thing. once we have a third, a trinomial and a binomial, I'm going to underline each of these guys. The way I do this is I multiply x by all of the thing, all of the trinomial that it's multiplying. So we have x, this first guy, times everything. And then, so that's the first bit. And then we've got the plus 2 times everything. So here's the plus 2. Maybe I should use a different color. Let's use blue. We have plus 2 times everything. And so the red thing, x squared minus 2x plus 4, that trinomial is going to get multiplied by both x and by 2. And then we add those things together. So the first one, x times x squared minus 2x plus 4, that's going to give us this bit right here. X cubed minus 2x squared plus 4x. And then the other part, x2 times x squared minus 2x plus 4, that's going to give us that part right there. 2x squared minus 4x plus 8. Now we combine all our like terms, and I want you to notice some magic happens. Some magic happens. Here we have minus 2x squared plus 2x squared plus 4x minus 4x. And so ultimately that's just x cubed plus 8. And so when you expand the polynomial, you're not actually changing what it is, you're just rewriting it in another way. This tells us that x cubed plus 8 is the same as x plus 2 times x squared minus 2x plus 4, that they are in fact equal to each other. And I want you to note that negative 2 is the only 0 from this graph. It's a little bit hard to see these axes, but I'm going to darken them a little bit. So here's our x-axis, and there's our y-axis. And you can see that there's only that 1 0 from the graph, because it's x cubed moved up 8. So we only cross the x-axis once. And so this tells us that here's our factor. Here's our factors as x plus 2. Negative 2 is the only 0. And so the rest of this, the stuff that's over here, x squared minus 2x plus 4, doesn't factor anymore. And you could test it out and realize that if you applied the quadratic formula, you'd get a negative discriminant and it doesn't factor. So there's no added roots to the to this polynomial from the quadratic that's there. So we factored it out completely. Okay, so this leads us to, if you did this a bunch of times, you might notice a pattern emerge over time. And the pattern is that if you've got a sum or difference of cubes, that it factors similarly to how you might factor a difference of perfect squares. The difference of squares factors into this nice a plus b, a minus b thing. A sum of cubes factors as well. It's just not quite as nice. You end up with a binomial, a plus b, times a trinomial, a squared minus ab plus b squared. And if you've got a difference of cubes, then you again get a linear factor, a minus b, and a quadratic factor, a squared plus ab plus b squared, left over. So these are actually very similar to each other. There's not a whole lot of difference between them, except the signs get kind of flipped around. The b squared stays positive and the a squared is positive. It's just that if you have a difference of cubes, you have a linear factor that's a minus b, and then everything is positive inside the trinomial. And if you have a sum of perfect cubes, the linear factor is positive, a plus b, and then you've got a minus with the middle term in the trinomial. So this minus and this plus go together, and then this minus and this minus go together. Okay, and then everything else is positive. So here's an example. Let's factor 27x cubed minus 1. So 27x cubed can be rewritten as 3x quantity cubed minus 1 quantity cubed. 1 is itself a perfect cube because 1 times 1 times 1 is 3. 3x times 3x times 3x is 27x cubed. I'll just write that out in case you're curious. 3x cubed is equal to 3x times 3x times 3x, which is 3 cubed times x cubed, which is 27x cubed. And so if we rewrite it that way, we can see that it is a difference of perfect cubes. We have 27x, or 3x as a, and so 3x is equal to a, and 1 is b. So we can plug those numbers into our difference of perfect cubes formula, and that gives us 3x minus 1. This is a minus b. And then we have a squared, which is 9x squared, ab plus ab, which is 3x times 1, plus b squared, which is 1. Okay? So that's the three terms. And if you were to FOIL this all out, which we will do next, if you were to expand 3x minus 1 times 9x squared plus 3x plus 1, you'd find all those middle terms cancel. We have 3x times 9x squared, 27x cubed, 3x times 3x, which is 9x squared, 3x times 1, which is 3x, negative 1 times 9x squared, which is negative 9x squared, boom, cancel. Negative 1 times 3x, which is negative 3x, boom, cancel. Negative 1 times 1, and that's negative 1. And so we end up with the 27x cubed minus 1 as we started. Okay, and so from this you could determine the root. There's 1, 0, and it's at 1/3. So if you set 3x minus 1 equal to 0, you find that x equals 1/3 would be the 1 root of this polynomial, this cubic. Okay, so now let's talk about factoring by grouping. So I would like you to take a moment and expand this out on your own. X plus 1 times x minus 1 times x minus 4. So pause the video, go ahead and write this out, expand it. If you're having trouble doing this expansion, remember you can always expand these two first, multiply them together, and then expand the answer against x minus 4. Okay, so, and I would do it in that order actually, because it will save you some trouble. So go ahead and do that, and then when you're done, resume the video. Okay, so the answer, if you multiply x plus 1 times x minus 1, you get x squared minus 1. So this part here is equal to x squared minus 1. And then when we multiply that by x minus 4, I'm going to write it all out. We have x squared times x minus 4, minus 1 times x minus 4, that's minus x minus 1. The 1 is hiding. It's there, but I don't write it usually. And now we just multiply each of these things together. We have x squared x is x cubed, x squared negative 4 is negative 4x squared, negative 1x is negative 1x, negative x. Negative 1 times negative 4 is positive 4. And nothing simplifies. We don't get any canceling or like terms. But we just showed something. That is that x cubed minus 4x squared minus x plus 4 can be factored like this. X plus 1, x minus 1, x minus 4. So these are the three zeros. Zeros are negative 1, 1, and 4. So that tells us what each of those zeros are. Now, how would you go about factoring something like this? Well, we just undo all those steps that we did up above. So this technique is called factoring by grouping. So to factor by grouping, the thing you want to start with is grouping the two terms aside. So you'll group the first two terms together and then the last two terms together. Now I want to make a note that this doesn't always work with cubics, but it works with some cubics, cubics that kind of nicely factor down. And so I'm only going to give you those kinds of cubics when we're doing factoring by grouping practice. So so you group those two terms. So all you're doing is just setting them aside or pushing them away from each other. So we've got 3x cubed plus 2x squared as our first two. I just put parentheses around them. And then we've got negative 6x minus 4, negative 6x minus 4 for our other two. Okay, now we factor a greatest common factor from each group. So from the 3x cubed plus 2x squared team, we can see an x squared is what's common. Whoops, don't want to use green, it's the colors. So we have an x squared that's common, and that leaves us with 3x plus 2 left. So that's the greatest common factor of 3x cubed and 2x squared. And then from the green team, we can see that both are divisible by -2, and that's the greatest common factor from negative 6x minus 4. So we'll pull -2 out. That leaves us with 3x plus 2. Aha! Once we've done this, we now know it can factor by grouping. So if what remained, which I'm going to highlight in blue, if what remained was not equal, if they both weren't 3x plus 2, it would not factor by grouping. And so if they are the same, they are 3x plus 2 and 3x plus 2, they are the same binomial, then you can factor the common binomial out. And here's where it gets a little bit messy and hard to see. So I'm just going to make a note over here, must the same to factor by grouping. So here's how we factor the binomial out. 3x plus 2 is common to both x squared and -2. So we pull a whole factor of 3x plus 2 out from both of those. So we get 3x plus 2 comes out in front. So there's our 3x plus 2. What's left is x squared and -2. And so we have x squared minus 2 from the greatest common factor from earlier. So x squared and -2 are what's left. And so we factor a binomial out. And this feels weird for a lot of people to factor a binomial, because usually we just factor, we do a greatest common factor gets pulled out. But we can do this. This is allowed. If this was like 10, x squared minus 2 times 10, we could just pull the factor of 10 out, all right? And then once you've done that, you try to factor the quadratic if it can be factored. In this case, you could factor x squared minus 2 down into x plus root 2 and x minus root 2, and you'd be done. And from this, you could determine the zeros. This is fully factored. There's nothing left. And our zeros would be -2/3 from this guy, negative root 2 from that guy, and root 2 from the last one. Okay. And that concludes factoring by grouping and the lesson for Monday. So I'll see you guys in class tomorrow.